There's two more things I wanted to share with you this week. Both of them figures that I thought were useful for understanding this bone stuff. One of these, this one on my screen right now, this is a comparison of the ultimate stress, which you know as the point on the stress strain curve where the curve maxes out, right? That point, that's the ultimate stress, of both cortical bone and trabecular bone in compression, tension, and shear. As a reminder, shear is like compression, except it's when the compressive forces are offset from one another. So shear is a very unusual force inside the body. We just don't encounter it that much, and which is probably why that bone is so weak in shear. So I like this figure because it shows that cortical bone, number one, is much stronger than trabecular bone, and number two is strongest in compression, less strong in tension, that's pulling apart, and weakest in shear. And then trabecular bone, areas of bone dominated by trabecular bone, are substantially weaker than cortical bone, which explains why a lot of the load-carrying bones of the body, like the femur, or the tibia, or the humerus, radius, ulna, why those are primarily cortical bone in the highest stress areas. Some people, a good example of maybe this difference, one thing that happens quite often in car accidents is people will fracture their pelvis because they sustain a very high force to the pelvis, which is a largely trabecular bone. And as you can see, that the pelvis will not be able to handle that the compressive and tensile forces induced by a high force nearly as well as, say, a cortical bone. So I just wanted to show this to show the differences in ultimate strength. Of course, we're not usually so interested in the ultimate strength because we want to stay down in this area in the physiological zone generally. But it does give you a general idea of the comparison between these different kinds of bones and different kinds of loading. And then the other thing I wanted to show you was a computational model that I ran this afternoon. And I'm going to explain to you what this is. So this is a cross-section of the humerus. That's your upper arm bone. So that goes from the shoulder to the elbow. And we're looking at a CT scan right here. That is it's like a slice from the middle. Technically, you know this term now, it's from the diaphysis of the humerus. So all of this in here is cortical bone. CT is very good at imaging cortical bone, and actually I think this is from a cadaver, and so all of the bone marrow on the inside is gone. But so this is the raw medical image, and the great thing about CT, and you know this from last week, the intensity of X-ray absorption is proportional to the localized density of the bone. So we can take this slice of the humerus, and then we can use the CT scan intensity to discretize it into little meshes, each of which has a different bone density. You can't really see the label on the axis here, but this is the whiter areas are more dense, stronger areas of bone, and the darker areas are less strong. So you could see this area right here, for example, is a less strong area of bone. And you can notice that the inner part of the bone is less strong, whereas the strongest stuff is on the outer perimeter. This is showing the distribution of bone density. We can see the greatest area of bone density is right here. And then what I did is I simulated how this cross-section of bone would respond if you applied a bending force to it. So what's happening is we're looking at the stress induced by a bending force. And so let me think about this. A negative stress would mean compression. So that means the compression is happening over here in the blue. And then tension is happening over here in this orange color. So it's like we're compressing the bone with a bending moment in that direction. Let me maybe redraw the humerus like this. So it's like we are bending it this way to induce compression right here and tension right here. So you can see the distribution of tension and compression in the humerus under this particular set of forces. And there's a few interesting things, one of which is by virtue of the fact that you have positive over here and negative over here, there's actually a little area of the bone that experiences no change in its stress at all. So that's very funny. And this maybe suggests to us why loading a bone in different ways will increase its strength, because we know that the degree to which bone upregulates its remodeling is going to be proportional to the stress, right? So presumably we'd get more bone remodeling here and less right here. So if we just loaded this bone with this same force over and over and over and over again, we might get some nice bone remodeling in this area and this area, but not so much here because it doesn't induce a lot of stress. Whereas if we bent it on some other axis of bending, we would get a different pattern. So that's one cool thing to show. Oops. The other thing I wanted to show you is that the areas of maximum tension and compression, those are noted with these little negative and plus signs. Notice how this happens at what kind of looks to be the thinnest part of the bone. That's not an accident. I mentioned a few videos ago, if you add bone out here, that makes the bone much more resilient, and it's no accident that we don't see maximum stress out here. And likewise here, this is also a narrower part of the bone. Maybe this part is narrow, but it's also closer to this negative axis of bending. The last neat little correspondence I wanted to show you was the positive marker here denotes the area of greatest bone density. So the single most dense, strongest area of the bone is right here. I don't think it's any accident that that actually happens to occur at the greatest area of negative stress. So probably this is the result of these kinds of forces, these kinds of stresses induced in the body. So anyways, I thought that would be a nice way to wrap up everything that we've seen for the week. So hopefully you've enjoyed these two examples, and hopefully you've enjoyed the content for this week, and I will see you next week.